All right, the question for Tim was from Don Banfield. Did you use saltation sensors? I didn't think they yielded impact energy. Is this a new feature? You also have to assume you know particle size, correct?
So Don, yeah, we use the saltation sensors. I don't know if that's a new feature. I mean, this dates back to about 2017, and so that was one of the things that was just standard with these sensors was both the particle counts and the kinetic energy. We do not have we do know what the particle sizes were, but that didn't seem to enter into the calculations. I'm not sure how that would fit in there as long as we know what the particle masses were.
Thanks, Tim. Okay, I think we got the live stream and everything going again. So as soon as they've got the slide shown again, then we can get back on track.
Are we on me now? I'm ready to go, but I thought I was at the end of the session.
No, not yet. No, we're having some technical issues.
In that case, time for coffee.
Let him share his screen instead. Okay, can you try sharing your screen instead?
Yeah, sure.
Thanks.
Still disabled, actually. Can you please give me the permission?
This is the one. This one. Yeah. Okay, we can do it from here, actually.
Oh, okay, that's fine. Yeah.
Can you see the?
Yeah, I can see it. That's
perfect.
Yeah.
Thank you. So, Abdullah and Zakharov, please.
Yeah. Okay. Hello, everyone. Actually, I'm very glad to be here today, and thank you guys for all this interesting information for about yesterday and Tuesday. Actually, all the summaries and discussions was very helpful and useful. So, in short, my name is Muhammad Islam. I am a geophysicist and research engineer at Moscow Institute of Physics and Technology, and researcher at a Space Research Institute of the Russian Academy of Science. Mainly right now, actually, our current work is study the geological and geophysical characteristics of the Moon and Mars, and under discussion right now, some new projects regarding Venus. Besides that, actually, we are studying the electromagnetic phenomena related to the dynamics of dust particles, and of course, creation of scientific instruments for measuring electric and magnetic fields, electromagnetic noise, and registration of dust particles on Mars, including here our devices, which exactly like my device, it's EMA. So it's electromagnetic activity. So our current research is to support two investigations: the lunar dust monitoring, which is in Russian PML, and the dust complex or DC. So both of them, they are projects Luna for Luna 25 and ExoMars. Of course, ExoMars right now it's under question, but Luna 25 it's still on board. In short, the BML experiments aim to investigate the dynamics of dust plasma in the Moon's near-surface exosphere, while the DC experiment aims to investigate the dynamics of microparticles of Martian soil floating in the near-surface atmosphere of Mars during both calm and dust storm conditions, which here our instrument EMA play an important role. Next slide, please. So in short, we can say that the electromagnetic activity measurement unit of the Martian atmosphere, EMA, is designed to register an alternating electromagnetic field in the frequency range from 0.1 to 1 megahertz. The unit registers the amplitude of the noise signal in the filter band of the amplifier. So a signal of this type can be seen as white noise at the output of a bandpass filter. So in the impact sensor unit, there is, as you can see here, and as you can see here, figure number 3. So it's 0.9 meter long antenna in the boom and an amplifier electrical board. So when using the signal generator, for example, like when we tested it, so the signal generator G637, we tested EMA device radio bath, and the sensitivity of the device input, like it was measured at a maximum gain of 90 decibel. So the device has a sensitivity of 7 microvolt and a signal to noise ratio of 6 decibel. So the radio, we can actually like say that when checking the sensitivity of the radio bath of the EMA device, the electrostatic discharge of various nature were generated. For example, like it was a laboratory measurements, for example, like silicon lighter, friction of an ebony stick, or movement of dry sand. And I was planning actually like to test it in the field yesterday if I would be able to come, but I hope that I will do it in maybe in the future. And actually, like right now, we are planning to make some field tests actually like in here in the Egyptian desert. Still like we still didn't finish it yet, but hopefully like soon, and we'll be able to share maybe like more results with you. So actually, like the laboratory results represented some imitation of electrical phenomena in near surface dust formations. So with a radio gain of about 40 decibel at a distance of up to 1 meter from the EMA receiving antenna. So this discharge were reliably recorded. During the measurements, the results were recorded using digital oscilloscope, for example, in the laboratory. DSO 1022A, and it was like which imitated the ADC of the EMA device in this case. So in laboratory conditions, as you can see, so it's like it's in here, like for example in figure 4 and figure 5, it shows an example of recording a signal from EMA amplifier on an oscilloscope screen when exposed to an external noise electrostatic discharge. So that's it, and I hope that if you have any questions, please you can send me either by email or you can send me, like I will share my contacts later. Thank you very much.
Any questions? You're in the chat. Yeah, one question.
Hi, this is Brian. I apologize if I missed this. So have you deployed this in the field and measured signals, or is this still in the lab?
Actually, like till now, because like in Russia, the weather is not on our side. So till now, we basically made like all of these results. It was laboratory results. That's why I'm planning right now to make any cooperation, for example, with any of the universities in US or Canada, or maybe here in the Egyptian Space Agency, just to make some field experiments in the desert, because I want to test it. Actually, like it was supposed for this device to be launched in August or September 2022, but of course, as you know, like it's a bit like maybe delayed. So till the time, I hope that I will be able to make some field tests, which will make our give me at least like in my research some confirmation results. But like the laboratory test till now, it's like it was very promising, and the device actually like show us some good results regarding the electrodynamics of dust particles on the Martian surface.
Thank you, Mohammed. We have to move to the next talk by Don Benfield.
Yeah, thank you.
Okay, cool. Yeah, so this is actually the other talk. I can give that now, but it's not an instrument one, it's a mission
we'll
one.
switch to the other one. Just a second.
This one.
Is that the correct one?
Yeah, that looks good. Thanks. Right. So I guess I was just going to try to tell you guys briefly about two instruments that we're developing. One, many of you may have heard about before, the sonic anemometer for Mars that we're working on, and another one, a fairly sophisticated saltation sensor. On the left, I have a few words about the sonic anemometer. You can think about this as basically being the equivalent of a commercial terrestrial sonic anemometer, but that works at Mars. It's pretty tricky to make that happen. The thing that we're doing differently is instead of using piezo transducers, we use broadband ultrasonic capacitive transducers. I just lost the slide for mine.
Yeah, just a second, please.
Okay, so just to keep going on that, it's about a half a kilogram, a half a watt, and it samples at about 20 hertz, which is what typically terrestrial ones work at. temperature sensitivity about 1/10 of a Kelvin, and wind sensitivity down to about 5 centimeters per second, maybe a little bit better. If you've got an application where you want it to be simpler, you could make it 2D as well, but usually we make it 3D. So I mentioned the fact that it uses these broadband ultrasonic transducers. We recognize that, well, one advantage is that they're very robust against noise. So unlike piezos, which just ring when you hit them or when you excite them, these have broadband behavior. So you can send coded signals across, and if, say, sand hits the face of them, then it's robust against that. But you can also use them to detect sand impacts or grain impacts. And because it has a very sophisticated response, you can not only tell when an impact happens, the energy of the impact, but also the momentum of the impact. And if you put another sensor at the base of the transducer, you can figure out the height that the impact came in at. So that's our saltation sensor that is now about TRL 4. We should be at TRL 5 in about a year. And we're going to put in a Matisse proposal in a week or so, and hopefully have it to TRL 6 in late 2024. We developed these little BB guns so that we can shoot well-known particle grains at the transducers to calibrate it as well. So we should be able to prove this works quite well, but we're going to also test it in the field. That's it.
Thank you, Don. Any questions? Tim has a question here.
Yeah, Don, this is Tim Titus, USGS. Can you expand a little bit more on how you would get the saltation profile as a function of height?
Yeah, so I mean, we haven't finished the design of the transducers themselves, but they're maybe 10 centimeters tall by a centimeter or two wide. And you could put a stack of them vertically, but each one of them will resolve the height that each grain impacts at. So just from one transducer, you could get some sense of the vertical profile of particle impact rate, particle speed, and particle size. So at least in some sense, just one transducer could give you some indication of the profile. But I think it's kind of an experiment design question of exactly how you implement this on a spacecraft.
So in principle, you could stack these with your sonic anemometers on a mast or a pole and get a really nice profile of both the wind shear and the saltation cloud.
Absolutely, yeah. And I forgot to mention, we designed it so that the instrument backend would be common to the two, so you could save some mass and power that way. So you could probably do this whole thing for less than a kilogram.
Can you stick in temperature and relative humidity and pressure?
Well, temperature already comes from the sonic anemometer with quite high precision. Pressure is just a few grams, 30 grams or something. Relative humidity, honestly, I don't think anybody should measure relative humidity. You should measure absolute humidity. And you can do that pretty easily with a TLS that Scott Rafkin is probably going to talk about in a little bit. And that also is well under a kilogram. So you could probably do this whole thing for less than 1.5 kilograms for everything that you just asked for.
Okay, thank you, Don. I will move to the next talk by Chide. I'm pronouncing it incorrectly.
Yeah. Hi, everyone. My first name is Baptiste.
This one. Baptiste, the stage is yours.
Yeah, thanks so much. So good morning, folks. So I'm Baptiste. I'm currently postdoc at the Los Alamos National Laboratory. And following Don's presentation, I'm glad to keep presenting you the potential for the acoustics for planetary exploration through the first sound that we have recorded very recently on Mars with the Perseverance microphone. So, well, for sure, the solar system is kind of a quiet place, but of course we have Mars, Venus, and Titan that have an atmosphere dense enough for acoustic wave to propagate. And in planetary science, we know less the acoustic spectrum compared to the electromagnetic spectrum, but actually the acoustic spectrum, especially in the audible range, it records most of the surface atmosphere interaction phenomena that we have discussed here on Tuesday. And so thanks to the SuperCam microphone that we have currently on Perseverance on Mars, we were able to record the high frequency dynamic of the atmosphere of Mars. Especially we highlighted new regimes of the turbulence. I think David will talk about that in more details. And also we highlighted some large and rapid temperature fluctuations due to the very short time response of acoustics and also the very high sampling frequency of acoustics. We are also able, with known sound source at the surface of Mars, as we use the laser-induced acoustic signal from the SuperCam instrument, we are able to constrain the sound propagation properties of Mars, and that gives us information about the atmosphere itself and its composition and its thermodynamic properties. And well, microphones are very useful instruments. They are low weight, low cost instruments, and we can have access to this high frequency content that is required for these new measurements we need for surface atmosphere interactions. So there are great perspectives for this new technique, acoustics, for Mars, of course, but also for Titan. And I think maybe Ralph will talk about that later, but we currently have, we will, I hope so, have one microphone, part of the Dragonfly mission to record this fantastic soundscape that we can have on Titan. So I think that's it. The poster is available on the website, and I'll be happy to take any question. Thanks so much.
Thank you, Baptiste. Any questions here or in the chat? So thank you again. And we're going to move to the next speaker. We did not receive a presentation for David Maymoun.
Yes, I apologize for that.
Can you share your screen? Is that something?
Yeah, sure.
Okay, perfect.
But you have to allow sharing.
Can you try sharing your screen now?
Yeah, do you see the screen?
Yes.
Okay, this is a kind of a follow-on of what Baptiste said. Actually, the idea here was to extend a little bit the sonic interest to from infrasound to sound recordings for the surface atmosphere considerations. In our group, there are several interests for solid Earth and atmosphere coupling coming from the atmospheric counterpart of seismic activity to more detailed modeling of what happens in the ionosphere when something happens, when an energetic event happens on Earth, on Mars, or on another planet. This came to us actually as a consequence, as first consideration, because when we first designed the seismometer from Mars, we just considered that Mars was dominated by the environmental noise, which was the atmosphere. So we had to dig a little bit into that. And the first things that we realized is that studying the noise of the seismic noise on Mars was basically studying the atmosphere and studying more specifically the turbulence. So we had to dig a little bit into that. And the first requirement set on the instrument, on the pressure instrument on In-Situ, were actually to get ideas about the high frequency, actually of the turbulence behavior of the Martian atmosphere. As you see here, we had to model that. Following these things, we went deeper and deeper into the interest of subsurface sounding through atmosphere, and then we were able to get the joint inversion of ground and atmosphere properties in order, to analyze the idea, to analyze the results of the vortices passage. So this is a work that has been done mostly by Naomi Murdoch and others. And so we are now, we see very much this coupling. So while we still interested in solid Earth, the atmosphere counterpart is very important to us because it's actually very coupled to the properties. If we went, we also designed the microphone for SuperCam in the team. And actually, if the primary interest was more related to rocks, it came very close to us that we realized the complementarity of the measurements of this microphone with what we were looking for the turbulence. So now with In-Situ and with the measurements on In-Situ, we had the turbulence measurement up to 10 hertz, and over 20 hertz. Actually, the microphone helped us to get more data. So that's more like the interest that we were looking at. And now, as you see here, we went very at higher speed for the.
We have to move on. I'm sorry. So if you can conclude.
Okay.
Thank you.
Okay. So the perspectives are very interesting. So as you see, if you couple a microbarometer and a microphone, you will get the full range of things and a full range of experiments. And so from a quake impacts to saltation, going into these measurements helps us very much to record a wide range of phenomena. And so we are advocating the use of these experiments. Sorry for being a little bit too long. Thanks.
No worries. Thank you, David. Thank you. We'll move on directly, even though there's a question in chat. We'll try to take it later. The next talk is by Cremons and co-authors. Can you please stop sharing your screen, David? So perfect. Thank you. Can you see the screen?
Yep, now it's coming up.
Perfect.
All right, thank you very much for letting me speak here today. I'm going to be talking about the development of a lander LiDAR that I'm working on at Goddard Space Flight Center with some of my co-authors shown here. And this is a funded Picasso program in the middle of its second year to design a boundary layer profiling instrument. So what we're doing here is we have a LiDAR mounted on a lander or potentially a rover. It points up into the atmosphere at two angles, 30 degrees off zenith and 90 degrees with respect to one another. And it measures the laser backscatter signal. And what that allows us to do is get both atmospheric backscatter, so measure of the aerosol content in the atmosphere up to about 25 or 30 kilometers, depending on the aerosol loading. It also allows us to discriminate dust backscatter from ice by looking at the depolarization ratio. And then because of the wavelength we're working at, which is 1911 nanometers, we're able to do water vapor profiling using the dial method. So the last thing we do is we measure the Doppler shift of the backscattered light in both directions, which gives us vector wind profiles. So in the upper left of the slide here, that's showing all 4 or 5, depending on how you count it, measurements that we get with the system. And then the center there is just a photo showing what it might look like. Obviously, at 1911 nanometers, we're well into the infrared, so there's no visible light, but the laser beams shown there are pointing off zenith and 90 degrees from one another in azimuth. So we're doing a number of different things with a single instrument here. In terms of our measurements, at the moment, we're building up both the laser transmitter and optical receiver systems in the lab, and that's kind of what's shown in the upper right. In the middle there, that's the receiver system being built up. So we receive the backscattered light and we split the polarizations from one another to do the depolarized backscatter. We also split off half the light to do the water vapor measurement. And then we have different lasers that shift us on and off the water vapor absorption lines near 1911 nanometers. So that's what's shown in the bottom left there is the water vapor lines that we've chosen to measure for varying levels of precipitable water on Mars, ranging from 5 precipitable microns up to 50. And then on the far right, on the bottom, is the spectrum of anticipated water vapor absorption from Mauna Kea over a 1 kilometer path length. And so that's where we're going to take this instrument to test it in the field, hopefully starting in next February or March. We're still pinning down the travel details, but we're going to take this instrument up to the Mauna Kea Observatory where most of the water vapor is below us and it doesn't get all absorbed. And we're going to make some atmospheric measurements up there of wind and backscatter and water vapor So if you're looking for more information, you can check out the poster or the abstract, both of which should be available, or feel free to reach out to me with any other questions or interest. Thank you very much.
Thank you. And we'll move on to the next speaker to lack of time. The next talk is by Refkin and co-authors. Are you gonna? Okay, 100 minutes. Okay, please go ahead.
It's a abstract.
It's the one. This one.
Hi, so this is Alejandro Soto. I'm today speaking for Scott Rafkin, who couldn't attend this meeting. Could you? No, that's fine. So this is a tunable laser spectrometer. So someone, Don Banfield mentioned earlier that you don't really want to measure relative humidity. You want to measure water vapor concentrations directly. So this is an instrument that Scott has led the design of, development of, to do that precisely. So the basic idea, so in this figure 1 we're showing here, what you're seeing actually is mostly what you're seeing is an anemometer, commercial anemometer we had in the lab, but labeled in the picture towards the top is something that says fiber, and there's a little fiber coupled to a VCSEL laser diode, and then the red arrow is showing the direction the laser will shoot down towards the detector at the bottom. So you have this simple source with the from the VCSEL laser diode and detection on the other end, and what's happening is in between, as the laser passes through the air, any water vapor that passes through that laser beam, you're getting basically an absorption spectroscopy measurement. So you get to measure the actual content of, if you tune the laser to the water wavelengths, you get water vapor concentration. You can also get CO2 concentration. You can tune it for methane, whatever species that you want. So the idea of this was to have a compact system. It's similar in some ways to the TLS on Mars, except that one's inside the spacecraft attached to a larger suite of geochemical instrumentation. This is intended to be attached, as we show here, to like an anemometer hanging out in the wind. 1 minute, okay. So that you can take measurements coincidence with like a sonic anemometer measurements that allow you to get the wind measurement and the humidity measurement at the same point. You start getting fluxes. It allows you to start doing the eddy covariance fluxes. You can also use the CO2 measurements with this in combination with the sonic to improve the ability to derive temperature. I believe that statement's correct, but Don can correct me on that. So Scott has developed this. It's not only just in the field. If we can scroll to the next page, we've taken it, sorry, not just in the lab, we've taken it out into the field. So he's done 2 types of experiments in the field. One, he just put it out in his backyard. At the time, he lived up in the mountains a little bit and had it out there for over a year, operating just fine through snow, cold temperatures, hot temperatures, and collecting data on our commercial sonic anemometer. The picture here is that we also worked with the USGS and mounted it on one of their large towers up 30, 40 feet in the air, attached to their sonic anemometers, and collected data in conjunction with them, and showed that you get good quality measurements of the water vapor, whatever other species you want, in conjunction with the wind measurements. So this instrument is at a TRL of 6. Scott's ready to fly it to Mars at the first opportunity, and I think it would be really useful to getting the water vapor concentration in the atmosphere. And I think that's it.
Thank you, Alejandro. We'll move on to the last talk in the lightning session by Bauer et al. Bauer, was it open? Can you see the screen?
Yes, I can.
Perfect.
So I'm ready to go.
So you can go ahead.
All right. Hi, I'm Tim Livengood. I'm speaking for PI Dina Bauer and the Corgi team. Corgi is an instrument suite intended for the moon right now, confirming orbital remote sensing with ground information experiments, consisting of 3 instruments: SSOLVE, the submillimeter solar observation lunar volatiles experiment; AMP, the AOTF moon probe; and CLUMI, the compact lunar hydration and mineralogy explorer. Our goal is primarily built around water at the moon. but we are capable of operating in any low pressure planetary environment is the general concept. So Mars would be at the high end of our pressure regime, limiting us to just working on Mars, the moon, and a few 100,000 asteroids as possible targets. So hardly anything. You see our basic plan there is the sun illuminating water molecules in the moon's tenuous atmosphere. There's not much, but there's not zero. And our goal is to measure it. If you could move to the next slide. The three instruments, so S-Solve at the top is a submillimeter heterodyne spectrometer to look at the spectral absorption of water vapor on the path to the sun to get plenty of signal to noise on a few kilometer path, looking at a 557 gigahertz water line, 509 gigahertz HDO line, and at 2.51 terahertz, 2 OH lines. So we can look at photolysis of water in the atmosphere, or we still have the possibility that it's actually hydroxyl is hydrating the surface and emerging from the surface to give diurnal variability. AMP is an imaging spectrometer, fairly common now in use for lunar missions, to image the surface for the 3 micron hydration band at the long wavelength end, but also to get mineral identification for in-situ resource utilization purposes, and to establish the context in which we see hydrated minerals. And then finally, CLUMI is moving into a regime that we haven't currently explored very well from the surface of planets, a mid-infrared imaging spectrometer, again, that will give us a full 2-dimensional hyperspectral imaging with sensitivity to a 6 micron band of water, as well as in absorption in the surface, as well as, excuse me, the Chris Johnson feature to identify silicate minerals that are in the surface. Let's see, and last slide, please. And the goal in all this is to try to understand the whole process of the hydrologic cycle at the moon's surface. The hydrologic cycle we had no reason to believe existed 13 years ago, but it has become clearer and clearer that there is a process of surface exchange between the tenuous atmosphere and the surface itself, with hydrating the surface and water being transported. Our challenge being that all of the directional arrows in here for input processes, output processes, and cycling, we don't know the magnitude of any of those. And so the goal in Corgi is to establish measurements so that we're actually working in a regime in which we can do, for instance, theoretical calculations and understand the environment of the moon by having at least some constraints on how much water there is and how fast it moves around. And I will stop there.
Thank you. Any questions? You're in the chat for, I guess, any of our speakers. Can we take a couple of questions, or do we? Checking the schedule. Yeah, for maybe we can take the question for Baptiste maybe for now. Let's see where it is. So the question was, are microphones and audible acoustics currently or commonly used to measure saltation on Earth? That's for Baptiste.
Yeah, so I don't know if commonly is the appropriate term for that, but there are some Earth studies that presented instrument concept called saltiphone to retrieve the impact from grains on mechanical surface, and then to retrieve the saltation level. And maybe David, if he wants to chime in on it, but also as he presented on Mars, we can retrieve such a phenomena also with the microphone.
This is not regularly done because actually it depends. It's a very sparse measurement. Actually, we especially with the microphone on 2020 we're a little bit high, so we just recorded the micro some saltation in one time during an event, a special event. So I think that there might be other way which are a complementary measure with respect to cameras and things like that. It's more that helps constraints, but I don't think it's a reliable measurement so far.
We have one last question here from Jack.
I have a question for Dan. We had a lot of discussion for the sonic anemometer of how you get an absolute wind direction component on Mars. We know on Earth you have sonics with a built-in compass, but what do you do? What are you thinking about the reference plane on Mars?
That's a great question. So our instrument measures line of sight wind depending on where we're pointing our two transmitters and receiver telescopes. So we essentially use those to get our line of sight wind directions, assuming no vertical wind, or I guess we could assume some sort of vertical wind, and then we just take the horizontal component pointing off zenith, and then use those two scalar measurements to get a vector with respect to the instrument pointing. I don't know if that answers your question fully. Maybe I didn't quite get where you were going at.
Well, we actually have to move on to the next session. I apologize, but I want to thank all of the speakers. Thank you, Dan, Baptiste, and David for taking those questions. And I'm gonna hand the one back to Serena.
Thank you, Lior. And sorry, folks, to cut that off. Please keep it going in as we break into our small groups, because we'll be discussing further about these different instrument possibilities for collecting the needed measurements. All right. On to that one. Yeah, okay, so a reminder, we're dividing into the same groups that we had divided into for discussion 2. So we had dust lifting was the first one, surface roughness, which we've now named /shear, because from the discussions on Tuesday, surface roughness may not be actually what we want to be measuring, right? We want to be measuring shear. And there seems to be a lot of discussion around how to do that. So we'll let that all fall together in group 2. The third group was volatile exchange, and the fourth group is aeolian sand flux. So similar to Tuesday, we're going to divide up into the small groups. In room, I suggest maybe we just divide into 2 groups, so you guys can figure out how to do that. Online, Brian's opening up the breakout rooms, so please select one. And we are in this. Let's see. You can change your group if you like. Yes. We are doing this until about, looks like 10 Mountain, maybe 10:05. I think it's 10:05 Mountain. Trying to read my screen. $10 o'clock Mountain. So we have about half an hour. So we'll do the small groups, and then we have a break, and then we'll reconvene as the plenary. So, all right. Any questions?